Hello and welcome to our next episode of Minerva PLM TV. I'm Jennifer Moore, your host, and today we have back with us Dr. Martin Eigner from Eigner Engineering. Martin, thank you so much for joining me again.
Yeah, thank you, Jennifer, and hi, everybody. Let's start to talk.
Definitely. So the last time we talked, we of course covered your background and we discussed a lot about the evolution of product lifecycle management, touching on System Lifecycle Management, or SysLM. And today we're going to go a little bit deeper in that area with the basic concepts of engineering digitalization and the role of SysLM. To get us started with that, can you share really, what does digitalization mean? What are the basics and are there levels?
Yes. Okay, then we can start with the first slide. I think would be easy.
Perfect.
I think based on Corona, I think for many people, digitization and digitalization is becoming very important because everything what we are doing, talking with our grandparents via WhatsApp chat, and streaming, I think everybody has got an impact by digitalization. But I think the Americans, it's interesting, in the American or English language, we have 3 levels when we talk about digitalization. We start with digitization, and that's interesting. Digitization does really mean to bring paper on a computer. Mm-hmm. If you scan a paper, it's digitized, nothing else. Yeah, I think we did it since 20, 30, 40 years. I think this level is well done. So the next level is the level of digitalization. And when we talk about, I think digitalization is working in a lot of areas, in community and politics and in hospitals. I talk about engineering. And when we talk about engineering, digitalization means what we did since 30 years minimum. When we have a digital model, for example, a 3D model from CAD, and we are using this model, for example, for numerical control, for doing the fabrication stuff, or controlling an assembly line based on this digital model. I think this is a part of digitalization. We have a digital model, and we use the data from the digital model for the next phase of the product lifecycle. Of course, it is not a full digitalization of the full product lifecycle, but anyway, we did it. And the highest level, I think with the level of digitalization, we save money. To earn money, we have to climb up the triangle on the top, and that is really the digital business model. So when we build, for example, a service-oriented business model based on a digital twin, I think to make money with digitalization, that is the highest level. But digitalization is a prerequisite for the level of digital business model.
Absolutely. And with that, do you see a digital agenda, or what is a digital agenda?
Yeah, the companies in Germany and in Europe, everybody discussed about digitalization, digital agenda, or whatever. So typically when we talk about the digital agenda, then most of the enterprise, most of the topics are interfering with engineering. So we have when we talk about 5 levels, we have the smart product. Smart product does mean a digitalized product, for example, a mechatronic or cybertronic assistance tool for autonomous driving. Even we have level 2 or level 2.5, a lot of assistance is done by this mechatronical assistance systems. That is smarter products. The products has to be connected with sensor, with actors. They have to be intelligent, and they have to be connected with the internet. As you said, they are the 4 factors for a smart product. We need smarter production. That's the same. Smart engineering does mean smart products and smart production. We have to, I think Industry 4.0 is a very typical strategy to improve the production. I think for me, it was too strong oriented on production. I think what is the solution when we have a strong production with stupid products? So we need strong, smart products and smart production. So that is the kernel of engineering digitalization. We need smarter processes. I think when you see in Germany how we handle Corona based on facts, so the numbers in Germany to calculate the number of Corona infected people is done in the decentral health center based on paper, and the paper is sent per fax in the central office in Berlin. I think the Johns Hopkins University in the United States got more and better and earlier the numbers of Germany than Germany itself. I think processes, not only in community, all the processes in engineering, that doesn't mean configuration management, release management, change management, data exchange between customer and supplier. I think digitalization of processes, number 3. The 4th topic is smarter analytics. I think I'm quite sure everybody knows about big data and all this nice discussion, artificial intelligence. He would like, I think data, in former times, I think that was the, Jean-Michel was the sentence, oil is the money of the world. Now I think oil is good. Maybe we need, for the next 30 years, we need some kind of oil. But I'm quite sure in the future, data are the oil and the money of the world.
I think you're right.
Everybody tried to get data out of their product and to make money of that. I think what Google is doing and Amazon is done for 10 years. I think now the engineering companies are thinking about how their product is delivering data. Yeah, for example, a windshield wiper system is communicating the data from the rain sensor to the central national weather condition system. Yeah? You can sell the data. Yeah, I think data to collect data in the operational phase and to use the data to make business out. For example, predictive maintenance is one of this type. And then smarter humans. I think we have to change our mind. And to be very carefully and politically correct, I have to say, engineers are not the, I'm very carefully, okay, they have a strong behavior to be resistant against, against the future. So I think that is my personal feeling. So we have to be more smart. The organization must be flatter, more flattened, not high hierarchy. We need to collaborate more and more across companies, across divisions. Mechanic has to talk with electronic, to talk with software and so on. I think we have to be smart. Also, when the culture must be changed, we have to be more open. We have to have more respect against another division. So today we said, okay, we start with mechanic, then we throw it over the wall to electronic, this throws over the wall to software. And I think we have to work together. We have to build up a common digital interdisciplinary product architecture, and then we can work together. I think that is the 5 topics: smart products, smart processes, smart production, smarter analytics, and smarter humans. That is typical the starting point from a company when they have something in mind, digitalization or digital agenda.
That makes a lot of sense to me, and it's all really valuable. And I love some of the examples that you included in there with like the windshield wipers and the rain sensors, because as an avid car fanatic and driver myself, that's one of the features that I never would have really thought that I needed. It's like, how hard is it really to flip on some windshield wipers? But of course, now that I have it, I'm like, this is amazing. And it allows you to,
helps.
Exactly. It does. So with all of that, what would you say are the real obstacles to achieving all of those different goals? Is it the employees? Is it the organizations? Is it culture, or is it data?
I think we have talked about smart humans. We have to convince employees that digitalization is not bad for the employees. I think the problem is a strong digitalization. We have to be honest, a strong digitalization means we have to shift employment from the one area to the other. And so there is an interruption in the employment process, and we have to discuss this open. But we are not unemployed. There are a lot of discussion. For example, there's the Israel author Harari. I don't know whether you know him. Harari discussed what does digitalization means for people, for employees, for the community. And of course, everybody agrees that at the end, when everything is digitalized, we will have less work. But also industrial revolution at the end has shown less work. Many years, 100 years ago, people are working 5 days, sometimes 6 days, and 10 hours a day. With each revolution, we have reduced the working time. With digitalization, we will reduce working time real dramatically. But we discussed in Germany from the I think we have to convince policy to join the process. In Germany, we think about, for example, right now we discuss a 4 days employment and 80% employment. Yeah. And we have, based on a digitalization, we increase the productivity. And so we are able to pay for 20%. I think we have to think about what is our employment type in the future. I think that should be in parallel to the process of digitalization. So employment, to convince humans that this is a good idea, I think that's very important. I think the other topic is we have to change our organization. I'm so glad when I'm coming into a company and I find a chief digitization officer or digitalization officer, somebody who is able and who have a job to care about digitalization across all the boundaries inside the companies, across all the silos. I think out of the traditional hierarchical structured companies, we are not able to keep track or to enforce digitalization. So somebody on the C-level must be responsible for the job. And I think the software becomes more and more important. So we are faced with even the products. I think 100 years ago, we have pure mechanical products. Right now, in automotive, we have more of 50% of the value of the car is electronic and software. I think this will increase. So we have to shift in other education areas, and we have to think interdisciplinary. We have to think in systems and not in silos. I think that is very, very important. We have to change the culture. We have to change the education, external from the universities, but also internally in the companies. We have to change the organization. We have to make it more flat, and we have to guarantee collaboration across the departments and the divisions and the culture. The culture must be there. There must be somebody who takes care about the culture. It's a cultural change.
Yeah, absolutely agree with you. The people are at the center of it and helping them to reposition themselves and learn new skills and be, relevant well into the future with these new digital norms and digital agendas is super important to reducing that resistance and making sure that we have effective societies along the way. So with that, you kind of touched a little bit on how Industry 4.0, in your opinion, is more about like production.
Yeah.
But how does digitalization, correspond with IoT or IIoT, iOS, Industry 4.0, all of those, kind of commingling things that are happening at the same time?
I think it is fully synchronized. To the discussion start with IoT, Internet of Things. It's very old. It's 1999. Yeah? So it's more than 20 years old. And I think iOS, Internet of Service, comes 4 or 5 years later. So for me, it's interesting. Many things are 20 years old, and now we are exploring it. I think IoT was a starting point. Then we discussed in the United States cyber physical systems. I don't like the term cyber physical systems. That sounds so spacey. Like I call it cybertronic system, but it means cyber physical systems means more than mechatronic. I think we know mechatronic for many years. It's mechanic electronic software which are communicating internally. And when we talk about cyber physical system, I think it's not a revolution, it's an evolution. These systems are able to communicate via the internet. Yeah. I think we can, with my iPhone, when I stay in another town, I can control, I have cameras go-tos in my home, and I can control the temperature. I can open the windows and everything. So I think that is something we can do over the distance via the internet. We can handle products. We can collaborate with each other. That's cyber physical products. And cyber physical products, to be honest, is the basic of everything. When we talk about Internet of Service, we need cyber physical or cybertronic products. We need cars or other products which have sensors. They send sensors, the temperature, the vibration, whatever. I think, and with this data, we can predict something is broken or will be broken in a few kilometers. So predictive maintenance means we take care about the productivity of the product in the operation. I think that is everything. And then we have a lot of other things. In the United States, we have this Industrial Internet Consortium. I think that is very important. America has the a lot of industrial involvement in this industrial internet consortium in Germany. It's called Industry 4.0, but I think it's the same. There are big industrial organizations worldwide who are operating worldwide, who take care about smart products, cyber physical products, digitalization, iOS, and so on.
What is a
it's
typical? Yeah,
it's a huge
absolutely.
movement. Yeah.
So, what does a typical IoT or iOS solution look like?
We have a very, very nice one. The craziest one in Germany, when we would like to get money from the government for a research project, we have to call the project whether smart blah blah or blah blah 4.0. And the most crazy, because I was born in Berlin, and for me, when I visit Berlin, Berlin becomes more and more dirty. And we made the government a proposal, we call it garbage 4.0. That is, we work together with the cars who clean everything.
Yep.
Were driving along the roads and putting the stuff into the car. We made an optimization. We have a contract with a company who built up the boxes. The boxes has a sensor who are showing what is the filling degree of the trash. And so we can plan the way of the car based on the filling factor of the boxes, of the trash boxes. And that was, I think we can show that we save, for example, between 20 and 30% of the time and of course of the money. Typically, the base of an iOS or IoT project is we have a product. The product is equipped with sensors. We are using the sensor, putting together all the sensors, the sensor data, and then this critical term comes big data analytics. You will get tons of crazy data. We have to analyze the data. For example, if you have a washing machine, with 5 sensors, we can control the washing machine. But the sensor sends million and million data, so we have to select the right data. When, for example, if we have a stronger vibration, then we would like to look into the data should automatically select, oh, there's a problem, the vibration goes up. Maybe after 5 minutes, the torque sensor shows a higher torque. And then we know in maybe 3 minutes, your washing machine will be programmed. I think this is the miracle behind an IoT, iOS project is data out of the field, analyze the data, make the right decision. Right now, we are on the way, but we have not the full function of artificial intelligence to analyze. We get the data, but we are not able to analyze everything. I think that's a learning factor. I expect good solutions. We have some kind of solution, but I expect for the next 2-3 years that artificial intelligence will become a real important factor in connection with the data to build up the intelligence of data. Data alone. I think when I show you data from an airplane, you see a lot of diagrams, but you are not able to analyze. We need intelligence.
Right.
And
Yes.
that's I think that is the main factor right now. We need more. We need more research in artificial intelligence to make the right analysis of the many data we got out of the field. And then we have business models. For example, predictive maintenance is a typical business model.
Yes. Yeah. I already start getting alerts, on my vehicle. Hey, you're due for service, and it knows exactly how many miles I've gone, regardless as how much time it's been, because that used to be your little stickers on the window.
But Jennifer, I'm not quite sure when your repair station has not a lot of business. Maybe they send you a car. Hey, you have to go to the repair center to earn more. I'm not quite sure, but I think in the future it will be analyzed really.
Yeah, definitely. Yeah. So with those solutions that you've described, obviously another part of that is going to be the digital twin. What does that look like?
As a digital twin it's a buzzword right now. Everybody's talking about the digital twin. There are many discussions right now, and it's interesting. There's no final agreed definition what it is. So I can try to define it in my own, but we have to make a differentiation between the digital model. The digital model, for example, in the car is all the data we are for a specific car, for example, a Beamer, a 3 Series Beamer, all the data. In German, we talk talk about this with the 150% data. It is stupid. It may be 2000% or whatever. 150% means that, for example, if your car has no sunroof, then even the sunroof is in the digital model because another is able to select the sunroof. In a digital model from a car, from a variant product like a car, you have to think about the German car has 10 powered by 28 different solutions. All the data, all types of seats with leather, with textile, with Alcantara, with all colors, green, yellow, pink, or whatever, everything is included. All the different steering wheels with leather, without, all the assistance systems, sunroof, yes or not, two-zone air condition, four-zone air condition. Once again, many selections. Everything is in the digital model. So that's a full set of all the options you can select, and you can build your car out of this digital model. When a customer would like to buy a car in Germany, he puts an order. So he said, I would like to have a 3 Series Beamer, or we can say Audi, or to be politically correct, or Daimler, or Chrysler, or whatever, Fiat. And he said, I would like to have a 3 Series Beamer with 18-inch rims. I would like to have I would like to have black leather seats. I would like to have colored screens. I would like to have a sunroof, and I would like to have assistance systems for lane control and adaptive cruise control. So then, based on this configuration, an instantiated product will be generated. It's done by a variant configurator, and then we talk about, and at the time of production, your car is 100% specified. Then we have a 100% bill of material. Your car has a specific equipment, what you have selected, and then this car will be produced. I think in the United States it's a little bit different, but this is a typical instantiation, and this is the first level of a digital twin. We call it digital twin foundation or digital twin core. That everybody calls this bill of material as built. What you deliver is the as built bill of material. If you have a plant where you have a long delivery time, then maybe you have as built or as delivered. Yeah. So that is the first step of the digital twin, the as built bill of material. Then that is also the final digital twin. Then it depends from the business model what you would like to use from the digital twin. I think I talked with the CIO from Tesla, and he mentioned he is only interested in the connection between software and electronic, because he would like to use the digital twin to guarantee update over the air. Yeah? I think, for example, a windshield wiper, the blade of the windshield wiper, you can exchange your windshield wiper blade, so there is no interest from the OEM, from the car OEM, to keep track of the windshield wiper or the tires. Yeah, everything which is not interested for tracking should reduce. On the other side, we have to reduce it, the as-built bill of material, and sometimes we have to add data. Yeah? So I think at the end we have to build up and customized digital twin for the right business model. If we have predictive maintenance, you have to think about what we should track based on predictive maintenance, and this should be part of the digital twin. The digital twin is a type of a copy of the physical twin. The physical twin is the exact car. Yeah?
Yes.
And the physical twin and the digital twin, they have a cooperation. They have the same serial number, based on the same collection. And the digital twin may be less, or in some kinds it may be even more information.
Yeah, that makes a lot of sense to me. So when you kind of take a step back for a second, earlier you talked about education systems and the way in which we're going to be moving towards, smarter and different work processes as we move closer, to the digital twin, these systems, lifecycle management, and all of these other topics for today. So what would you say, really, besides the still siloed mentality that we have in the education system, what would you say the other issues are with achieving the right education to support this future business model?
Yeah, I'm working very long, and even when I was working for Bosch 40 years ago, I was involved in the education in German high schools, And I was always impressed by the silo thinking. We have mechanical education, electrical, electronic education. We have software informatic education, and that is. Then we start in the 90s or in the new century, we start with mechatronic. I think United States has started a little bit different. In United States, most of the technical universities, they have a curriculum called systems engineering.
Mm-hmm.
Yeah. In Europe, you will find only a few universities who are educating systems engineering. I think, of course, we need mechanical engineers, we need electronical engineers, we need software engineers.
Mm-hmm.
They are very deep educated in this division, but we need the people anyway. Even if a student studied mechanic, 20% of his education must be to understand what is the thinking of a software engineer, what is the thinking of an electronic engineer, because they have to know. Right now, they have no respect each other because they don't know how they are working. The electronic engineer, the software engineer, and the mechanical engineer they have totally different processes. For example, the mechanical engineer has a bill of material. The software engineer has trunks and merges, and so he has a baseline. We have a bill of material. So change management is totally different. Nobody is able to understand the other one. When you talk about baseline, oh, I have a bill of material, and I watched a lot of discussions between software engineers and mechanical engineers. I think the first prerequisite to work together is respect. And even the mechanical education should involve electronic and software. But I need maybe when we have 100% trained or educated engineers on the university, I would like to have around about 20% which are horizontal education. That is the systems engineer. The system engineer should learn about systems thinking, interdisciplinary thinking, and he should have maybe 20% knowledge of mechanic, electronic, and software. In my projects, when we talk about system architecture, sometimes I was more successful to use a mathematical educated or physical educated engineer instead of a mechanical engineer, because the mathematical or physical educated, even the chemistrist, is open. They have no blindness like a horse. They can think more independent. Yeah? And that's something I'm missing. I'm missing in the education, and even in the companies. We have a mechanical department, electronic department, software department. We need more system thinking, and we have to define a department which is responsible for the interdisciplinary system architecture. I think that is very, very important.
How do you think that's going to affect the future of design methodologies? Do you believe that we need new design methodologies? And if so, what does that look like?
I think the typical design methodologies in Europe, I think in the United States, it's nearly the same. We have design methodologies, they are created in the 60s, yeah? Especially in the mechanic. We have not, but right now we are working hard on my institute to explore a new interdisciplinary system-based, system architecture-based, system thinking-based design methodology. And I think that's something we should push, and we should put more effort in the research of this interdisciplinary design methodologies. Yeah.
Okay. So what about V models? Can you adapt these V models to move more in that direction? Like, what would that look like?
The V model was born in software design. Mm-hmm. Yeah, the V model is born in software design in the 60s, 70s from Mr. Böhm. And the V model is very good for software. You have the concept, and then you are doing the coding. But if you do the coding, then it's produced. In software, you have not a difference between development and producing. If you have developed the product, it's produced. So here you have the development on the one level, and on the other level, you have the testing. Yeah? There's no production. In mechatronic or cybertronic, you have the requirements, the system architecture, then you split into the divisions, and then you are building based on computer design, you're building the geometry, the code, and the electronic layout, and then you are doing the physical testing. But I ask you, where is the virtual validation and verification? Where is the simulation? When we talk about digitalization and virtualization, in the original V model is no space for digital or virtual simulation. And that makes me crazy, because to save money and to reduce the effort to develop a product, we have to do simulation as first as possible. Therefore, we have added small V's. And now I know what you mean. That's a small V. The first simulation is done in Simulink, in Modelica, in System C, in electronic. And then we are able, with a restricted geometry, we are able to validate our requirements. I think when you start with the development, you may have 5 to 10 different kinds of solution in your brain. And with your first simulation based on Simulink or Modelica, you can reduce the 10 solutions maybe to 3. Mm-hmm. And it's very important to reduce the many different possible ideas. And then you made a decision, yes, we take solution 1 and 2, and this will be done more in detail. Then we have, once again, we are building the digital models, mechanic, electronic, software. We do once again a simulation. Right now we are doing on the concrete geometry and the concrete weight. We are doing the concrete code, software, and the concrete function of the electronic. And once again, we can guarantee in the today's tools for simulation, we can guarantee 98% of the reality. So, and that's very important. I think when you start to build up a physical product, you need money. The virtual simulation is much more easier, it's repeatable, and it makes life much easier. So therefore, in our design methodology, we got some small V's inside, and that is the first virtual simulation, the second virtual simulation, and now we have the physical simulation at the end. Yeah. That's the difference. Yeah. But I think it's quite important, because when we started with mechatronics, it's, oh, nice, there's a V model, but this V model software will not be produced. That's crazy. Software, if you make a Java program, then it is produced. Yeah. Mm-hmm. There's no production process. Yeah. There's no assembly line or something like that. And therefore, for software, the normal way is okay. Yeah. It's good.
So, what would you say a design methodology then would look like as compared to mechatronic for the cybertronic?
I think that this is easier. It's, to be honest, it's the same. For me, it's the same. So maybe a theoretical professor will show it with me, but it's only the balance between mechanic, electronic, and software. I think a mechatronic product could mean 80% mechanic, 10% electronic, 10% software. Cybertronic has the same ingredients. It has mechanic, electronic, so it will have much more electronic and much more software. It will have much more communication. I think the electronic and software will shift to smart software and smart electronic with communication via the internet. And I have to say, what we have introduced is a fourth discipline. And I got a lot of critics that I have, after 100 years of 80 years, I have introduced a fourth discipline, mechanic, electronic, software. I said we need a fourth discipline, service. When we build up a product with the integrated service business model, then all the service related components must be integrated into development upfront. For example, if you have a car to share, you need an accounting system, you need a tracking system, and so on. Yeah. So it's a different car. So it's specially equipped. Or when we did this garbage 4.0, the trash box and the car, the truck, must be special equipped with the special electronic and software we need for executing the business model. Mm-hmm. So service, we are not able to build up a car and then we said, okay, we share the car and now we have to put it in a GPS system or an accounting system that will fail. So service is for me, we should start with service development in parallel to the system architecture. It should be included in the system architecture.
Yep, absolutely. And that definitely is a little bit of a twist on the design methodologies of today. So this has been really great. I have 2 more questions for you, and then we'll start to wrap it up here. But we've touched on a lot of topics from different digital agendas and design methodologies and all of these different things. One thing we haven't really touched yet is the idea of the digital thread and how that creates an integrated IT environment that helps, with the future objective of digitalization, digital twins, and all these other concepts. Can you talk a little bit about the digital thread? What is it, and that integrated IT tool concept?
Yeah, I think you have to keep together the digital model, the digital thread, and the digital twin. I think they are very tight together. The digital thread is, for example, it's always interesting. When I was responsible 5 years for the international change management inside Bosch, and that was a crazy job. We have companies in Bulgaria, in South Africa, in South France, in Spain, in Belgium, in Germany, in United States, in Brazil, and we produce the same parts and components and products. And the think about change management. When we discuss, we change the part in Germany, then we have to collaborate with all the other companies, and we have to deliver the customer in France. Maybe Ford has a company in Spain, in South Africa, and in Brazil. We have to guarantee that the part is introduced on the same day in all the 3 countries. So we have to think about a coordination of all these companies, and we have to collaborate, and we have to. It was a manual process. We have to phone each other. We have sent faxes and so on. I think that is very important, that in a global working enterprise, we have a common understanding how these processes are running. I think that is for me the first thing, and that is a digital thread. I think the tip when you ask somebody who is involved in change management, he has always one pain point: what is impacted by the change? The so-called impacted or affected items. I think based on DIN or ISO 9000 or 9001, each company has to define so-called configured items. Configured items, and that is very important for the digital thread. Configured items may be in an automotive company between 200 to 300. Configured items are all items we have to watch regarding a change. It could be a document, it could be a bill of material, it could be a specification, a requirement, it could be a numerical control file, it could be an MPP, a manufacturing process plan, and many documents and parts data, specification, and all this stuff. And then you have this 200 configured items. If you change, for example, if you change the document, you change the tolerance. Now, you think about all these 200 related configured items, which is impacted by my change. So, and that is nothing else as a digital thread. My dream is I hit on the screen my document 4711. And then I would like a nightmare or a miracle. I see all the configured items which are related. Yeah, that's very easy. Yeah, when we have a 3D, when we have a drawing, we change the drawing to tolerance. Then I think the first is we have a 3D model. Of course, we have a part item. Of course, we have a bill of material. I think this item is used in other components, assemblies for different customers. We have requirements belonging to that. We have maybe a functional breakdown, logical breakdown. We have a process plan. We have maybe quality information. Maybe this part, but you are just trying to change, is involved in another change operation. Yeah. In Bosch, I did nothing, all paperwork. And this is a digitalized digital thread is exactly point to the material number, item number, and you will see all the configured items. We have no automatism right now, but I'm quite sure that maybe a potential solution based on artificial intelligence in the future. Right now, I can see all the impacted items. This is included, this is impacted or affected, this is affected, this is affected, this is affected. Yeah, and then when you have an engine change order or request, You have the so-called affected matrix or impact matrix. All the parts and documents belonging to the change, they are included in the impact matrix. Yeah? That is a digital thread. The connection between different, I think along the product life cycle, you have requirements, you have function, you have logical breakdown, you have behavior, you have test cases. In the system architecture, you have stakeholder, then you have the mechanical BOM, the electronic BOM, the software trunks, and then you have to build a mechatronic bill of material. Then you start with the M-BOM, the manufacturing BOM, the manufacturing process plan, maybe a plant simulation, assembly line simulation, and. During the product life cycle, you are generating thousands of information. And to find, when you hit, it's a very big, we call it semantic network. It looks like what the spider is doing, this net. You hit one node and you get all the other information together. Digital thread. Yeah. The digital connection. Yeah.
And the digital thread, the visualization and the ability to go back and forth along the trail and see all the impacted items and the configured items, that's such a huge leap from, where we were when you were at Bosch. But hearing about the future of the automation and the possibilities that exist with AI is so much more exciting and even greater leaps and bounds. So looking forward to that. So all of this culminates into the capability to add the system lifecycle management as part of the overall operational chain of the product lifecycle.
Yeah.
Have you done a validation or a verification of this concept?
I think we have. I think no company worldwide is doing 100% of this vision. Nobody. We have projects in Germany and in Europe was starting to get to, for example, especially the system architecture. I think the digitalization, the borderlines between different areas requirements are totally fragmented today. The system architecture is starting right now in aerospace, defense industry, automotive industry. I'm very proud that we can see that system architecture is ramping up because system architecture and requirements are tightly connected. Now we have the possibility to read the requirements. There's an international standard, RegIF, that we can start to connect requirements to function, logic, and behavior. And from the logical breakdown, we are very close to the general EBOM, engineering bill of material. The next battle between, or on the border, is between the engineering bill of material and the manufacturing bill of material. It's a crazy battle. Typically, the one is in the MRP systems, the one is the other is in the PLM system, and ours has a wonderful solution developed. Normally, you have a triangle. You have the EBOM, you have the MBOM, and from the MBOM, you are derivating the bill of processes, the MPP, the manufacturing process plan. The funny story is, you have to keep in mind, each CAD system delivers a structure, a mechanical CAD structure, electronic CAD structure, or software structure. We have structures even in the early phase of development. We have to build these structures together to a mechatronic bill of material. Then we have to transfer to a manufacturing bill of material, another very similar structure. When we have the same product in 3 countries, in different factories, we will have 3 another manufacturing BOMs because the supplier situation, the resource situation is different. So we have structure. And as more we have redundant structures in the company, as more it is complicated to build up a digital thread because we have a lot of redundancy. And therefore, the idea from ours is to generate the MPP, the manufacturing process plan, direct from the workbench, from the EBOM, with drag and drop, to connect the resources, the skills, and everything. And then, as a result, we can generate, when we do this, we can generate the MBOM automatically. The MBOM is not a fixed stored new structure. The MBOM is the result, the generated structure of the product out of the MPP. And the question is, do we need an MBOM? I think we have to think different. So we have, at the end, we have to reduce the complexity of the product life cycle and the processes. And so there are some very good ideas to generate the MPP, to get rid of a defined MBOM. We can generate the MBOM. And the question is, do we need an MBOM for the future when we have a manufacturing process plan? Because the structure of the manufacturing process plan and the MBOM is 100% the same regarding the parts and components. Yeah? And then the next big step is, when we have the product, how can we go to the digital twin? And I see projects, for example, we have some projects in Europe starting with system architecture. I think we are not able to deliver the full process. We have the software to do this, but no customer will survive it. So we have to start carefully. Maybe we have customers in Germany, we start with MPP. So we start with a tight connection between PLM and simulation. Even the simulation of the assembly line will be done in hours, based on the MPP. The MPP is connected to the cost center from SAP, MRP, and so we get all the information we need, but the simulation of the assembly line is done out of hours. So we are shifting function out of the MRP system into the PLM solution right now. So to answer your fear is, we have not a customer who is doing everything. We have customers working on the digital twin area. We have customers working on the tight integration of production, manufacturing, and controlling it from PLM, because PLM is more flexible, more agile, more scalable as an MRP system. And customers are arguing. So at the end, I see MRP in a lower role in the future. I see PLM and MES, manufacturing execution system, in a tight connection. And the customers who are really working interdisciplinary, they are focusing on the system architecture and integrating the requirement. I think there are 3 areas, and maybe if you ask me in 2 years, then we may merge these 3 areas to one big customer project. But we have the software is there to guarantee the solution for the whole product life cycle. Yeah.
Well, this has been really fascinating, Martin. Thank you again so much for joining me today.
Yeah, I enjoy it. Thank you, Jennifer.
And I look forward to hearing in 2 years where you guys have gone with with these concepts and many more topics in between. And of course, to all of our viewers, thank you so much for joining us. Like this content, remember to hit the like and subscribe button so you'll be alerted to future content and you'll never miss an episode. Have a question that you'd like to see answered, especially for Mr. Eigner, drop it below in the comments or send me an email at jmo@minerva-plm.com to see that answered in a future episode. Thanks so much, everyone, and have a great day.